Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lectures we have discussed about the mass transfer theory. First of all we discussed the film theory, after it we discussed the two film theory, then we discussed the penetration theory, and at last we discussed the surface renewal theory and boundary layer theory. So in various theories there is a relation between the mass transfer coefficient and the diffusivity. Relation between mass transfer coefficient. Relation between mass transfer coefficient and diffusivity from various mass transfer theory. In the first theory, which is the film theory, we discussed that the molar flux of component A is directly proportional to the concentration gradient, or we say that molar flux of component A is equal to minus diffusivity of component A in B into change in the concentration of A with the z direction. And we also said that the minus dAB divided by delta z is nothing but length, and that is the dCA, or NA is equal to dAB divided by length into minus dCA. This dCA, suppose this was equation 1, and we know that molar flux is nothing but it is K into change in concentration. So suppose this is equation A and this is equation 1. So from equation A and equation number 1, by similarity, by comparing the equation A with equation 1, we will get that this is the mass transfer coefficient. That the mass transfer coefficient is nothing but it is equal to dAB divided by L. If we compare the two equations, so this is the NA, this is the NA, this is change in concentration, this is change in concentration. So this K will be equal to, if we compare two equations, then K will be equal to dAB divided by L, and K is nothing but the mass transfer coefficient. So from the film theory, we know that the mass transfer coefficient is directly related to the diffusivity of component A divided by L, or K is equal to dAB divided by L. So mass transfer coefficient is directly proportional to diffusivity of A in B to the power 1. This is from the film theory. So from the two film theory, we said that there are two films, the stationary liquid film and the stationary gas film. The solute work was transferred to the stationary gas film, then it passed through the stationary liquid film. We said that at the interface there is no resistance to the mass transfer. So we said that at the interface there is steady state process, and at the interface the diffusivity of component A and B divided by L, which is L1, which was equal to this is, and the change in concentration Ca1 minus Cai. This is the Cai, the concentration at the interface, is equal to the diffusivity of component A in B divided by L2, and this is the Cai minus Ca2. So from the two film theory, we said that this was a flux. That flux which comes to the interface from the stationary gas layer is equal to the flux which passes from the stationary liquid layer. So we said that the component was transferred, that at first the component was transferred from the bulk of gas to the stationary gas layer having thickness L1, the diffusivity of component A in component B is DAB, concentration of component A in the bulk gas, concentration of component A in the liquid gas interface. So we said that at first of all the component was transferred from the bulk of gas to the stationary gas layer. So this is the mass transport in the stationary gas layer. This is this one. So we know, we said that the mass transport, that the mass which transferred to the stationary gas layer was equal to the mass which transferred to the stationary liquid layer. So this is the mass transport through the stationary liquid layer. This is the thickness of the liquid layer, diffusivity of component A and B during its movement in the liquid layer, the concentration of component A at the interface, concentration of component A in the bulk of liquid is Ca2. Similarly, the concentration of component A in the bulk of gas is Ca1. The concentration of component A at the interface, gas liquid interface is Ci. So from this two film theory, we said that if we suppose if this is equation 1 and this is equation 2, this is the general convective transport equation. This is equation 2. So if we compare equation 1 and 2, then this is the concentration change. This is change in concentration. DAB divided by L is equal to K, and this is Na. So if we compare equation 1 and 2, then it also says that mass transfer coefficient is directly proportional to the diffusivity of component A, either L1 or L2. L1 or L2. If we compare this equation with this equation 2, or if we compare this equation with equation 2, we will get that K mass transfer coefficient is directly proportional to the diffusivity of component A and B to the power 1. So from film theory and two film theory, we said that mass transfer coefficient is directly proportional to the diffusivity of component A into component B to the power 1. So in the, similarly from the penetration theory, we said that the mass, that the molar flux of component A is equal to the diffusivity of component A and B divided by the pi, which is 3.14, and the contact time and change in the concentration of A, which is Cai minus Cab, concentration of A in the bulk, concentration of A at the interface. So suppose this is equation number 1 and this is equation Na. Molar flux is equal to K into change in concentration. So suppose equation 2. So from equation 1 and equation 2, if we compare, this N is equal to Na, this is equal to this number. So K is directly proportional to diffusivity of component A into component B divided by alpha into contact time under the root. So in this penetration theory, that showed us that the mass transfer coefficient is directly proportional to the diffusivity of component A in B to the power 1 over 2. R K is directly proportional to DAB under the root, under the root. Similarly, there was another theory which is called the surface renewal theory. From the surface renewal theory, we obtained molar flux equation for molar flux, which shows that molar flux is directly proportional to the diffusivity of component A and to fractional of surface area renewal. Fraction of surface area renewal per unit time. This is the fractional of surface area renewal per unit time. S is the fractional of surface area renewal per unit time, having the unit of 1 over second or 1 over time. So from this was Na, which is DAB, diffusivity of component A into component B into the S. And suppose this is equation 1, and suppose we have another equation which is K into change in C. So this is Na dAB into S. Suppose this is there is also some concentration. Suppose this is equation 1 and this is equation number 2. So from this equation 1 and 2, we know that Na is equal to Na. If we compare equation 1 and 2, and dAB into S under the root will be equal to K, and this is change in concentration, this is change in concentration. So it shows that mass transfer coefficient is directly proportional to the diffusivity of component A into B into S. So again, from this equation we know that mass transfer coefficient is directly proportional to the diffusivity of component A into the component B divided by 1 over 2 R dAB under the root. Mass transfer coefficient is directly proportional to dAB under the root. So again, mass transfer coefficient is directly proportional to diffusivity of component A into B to the power 1 over 2, just like in the previous theory, which is the penetration theory. Similarly, there is another theory which is the boundary layer theory. We have discussed the boundary layer theory in the previous lecture, which is very important in the transport phenomena, in the fluid mechanics, in the mass and heat transfer. So from the boundary layer theory, we know that the Sherwood number is S is denoted by SH, which is equal to the K, which is the mass transfer coefficient, into the X, the length along the plate, and this is the mass transfer coefficient X, and there is another K divided by diffusivity of component A into the B. This is the Sherwood number. So the local Sherwood number is XO, which is equal to the local mass transfer coefficient into the X point and to diffusivity of component A into component B. Similarly, the which is equal to 0.332 Renewal number to the power 1 over 2 and Schmidt number to the power 1 over 3. So this is the local Sherwood number. Similarly, we know that there is average Sherwood number, which is average Sherwood number, which is K, average mass transfer coefficient, and X and L, which is the total length of the plate, and to the diffusivity of component A and B, which is nothing into but 0.364 Renewal number 1 over 2 and Schmidt number 1 over 3. Now suppose this is equation 1 and this is equation number 2. Now local Sherwood number is equal to 0.332 Renewal number 1 over 2, Schmidt number 1 over 3. So again, the Sherwood number is Kx into X into dAB, and this is the constant. Forget about this. This is 0.332 Renewal number under the root, and to Schmidt number is nothing but mu kinematic viscosity divided by diffusivity. So kinematic viscosity divided by kinematic viscosity 1 over 3 and divided by diffusivity 1 over 3. So the diffusivity come to numerator and it become minus 1 over 3. So now this is Kx, this is Kxo, and this is the Xo, and this is the 0.332 Renewal number under the root, kinematic viscosity 1 over 3 and diffusivity A, and this diffusivity come to this side, so this is minus 1 over 3 plus 1. So again it is 0.332 Renewal number. Okay, this is under the root R1 over 2 to the power 1 over 2. This is kinematic viscosity to the power 1 over 3, and this is 3 minus 1, 2 over 3 diffusivity 1 over 2 divided by 3, 2 divided by 3 because 3 minus 1 2 and divided by 3, so 2 2 divided by 3, and this is k. So in this, from this equation, suppose equation number 4, equation 3, suppose. So from this equation, k is directly proportional to the diffusivity of a and b to the power 2 over 3. So from the boundary layer theory, similarly, this relation can also be obtained from equation 2. So from the boundary layer theory, we know that the mass transfer coefficient is directly proportional to the diffusivity of component A into the component B to the power 2 over 3, as we obtained from equation number 2. This equation can also be obtained from equation number, this relation can also be obtained from equation number 2. So it is average Sherlock number. Newton 0.4, renewal number, Smith number, not 3. From this equation we can also say that k is directly proportional to diffusivity of component A into B 1 over 2 over 3. So this is from the boundary layer theory. The boundary layer theory show us that the mass transfer coefficient is directly proportional to the diffusivity of A and B to the power 2 over 3. So as a summary, the summary show us that from the film theory show us that k is directly proportional to the diffusivity of A and B to the power 1. The penetration theory show us that the k is directly proportional to the diffusivity of A and B to the power 1 over 2. The surface renewal theory shows that k is directly proportional to the diffusivity of component A and B power 1 over 2. And the boundary layer theory shows that k is directly proportional to the diffusivity of A and B to the power 2 over 3. Similarly, the two film theory also show that the two film theory also show that k is directly proportional to diffusivity of A and B to the power 1. So just like the film theory. So these are the relation between mass transfer coefficient and the diffusivity. The main parameter in the film theory and two film theory is the thickness of the film. Similarly, the main parameter in the penetration theory is the contact time. The main parameter in the surface renewal theory is S, fractional of surface area removed per unit time. The main parameter here in this theory is the thickness of the layer, whether it is boundary layer, concentration layer, or thermal layer. So, and the ratio of these layers gives us the Schmidt number. So, it is all about the boundary layer theory and other mass transfer theory. And in these equations show us the relation between the mass transfer theory, mass transfer coefficient, and the diffusivity, which we obtained from various mass transfer theory. So if you are new to the channel, please like and subscribe. Thanks.